long slot, 45 minutes, we split it in two. I am Paolo Bientinesi, as Christina said. I'm the director of the HPC2N Computing Center. Yes, I'm also professor for high performance computing. And I will talk about 15, 20 minutes. I will actually go rather fast and stay high level. And then Pedro will give a demo. Let's see if I manage to move forward. Yes. So first of all, let me say a few words about the center. HPC2N is a Swedish supercomputing center, which is just right here in our basement. And it's one of the SNIC, Swedish National Infrastructure for Computing. So it's one of the SNIC centers. It offers both large-scale computing and large-scale storage. It has quite some history, and it's a partnership with other 4 universities and institutions. The mission, as I said, is to provide the state-of-the-art resources, but also expertise. So I will make this distinction. Resources is hardware, expertise, it's people. Resources, the main resource has been Kebnekaise. This is a supercomputer, or at least it was a supercomputer. Now, you know, supercomputers have a lifetime of about 5-6 years. And so this is getting a little bit on the older side. So we're working on the replacement. Hopefully we will be awarded one. This is me pretending to be doing some work in front of a storage system. This is where data sits, and both for computing system, so for Kebnekaise and for the storage systems, users can ask for allocations, and they come in a small, medium, large allocations. Small, anybody can get, doctoral students, anybody. For the medium and especially for large, the process is much more involved, but pretty much everybody can start and then ramp up, showing what they need these resources for. I don't want to get into details. I just want to say that Kebnekaise is not a lot of one type of processors. It's heterogeneous, so it has an offering for different type of users. If you need a lot of memory, not so much memory. If you need the few cores, a lot of cores. And similarly, it has an assortment of nodes with the GPUs, again, for different needs and different tastes. This is just to say that there is a little bit for everybody here. And then switching to the other resource that we talk about, these are human resources, and we offer application experts. So specifically, we have 4 people that can assist the users in different application domains, but also in different programming paradigms and different parallelism schemes, and so on and so forth. And these people, but not only them, we offer collectively as a group, we offer user support. Basically, we hold the users' hand, and then we try to make them advance the expertise ladder when it comes to computations. There are training programs, education programs, and then there are more advanced workshops and seminars on a range of topics. From programming languages and to tools for programming, but also application-specific workshops like molecular dynamics, machine learning. Okay, and I want to debunk, probably several of you are thinking, well, this is probably not for me, it's for experts only, it's only for people that have a lot of computation or that have a lot of data to deal with. And so I want to sort of debunk this assumption. I want to postulate what I call the fundamental axiom of high performance computing. This is tongue-in-cheek. Don't go and look it up. It's not a theorem. It's something that I came up, or that I named. But the fundamental axiom is that every computer is a supercomputer. So even if it doesn't fill up a whole room or a whole basement, a computer is still a supercomputer. In fact, your laptop or my laptop are supercomputers. And I'm not joking about that. There is a ranking, it's called the top 500 ranking. This list is put out twice a year, and it keeps track of the fastest 500 supercomputers in the world. The triangles here, this is okay. On the y-axis, you can imagine this as a speed. If you imagine cars, this is how fast the cars go. In practice, these are computers, and this is how many operations per second these computers can perform. These triangles monitor D1, the top, the fastest supercomputer in the world, over time. So the fastest supercomputers nowadays, it's not yet able to perform 1 exaflop per second. 1 exaflop is some incredibly large number of operations, I think 10 to the 15th, something crazy. And this number here is the 500th supercomputer, and the green is the top 500 put together. And in this plot, if you draw the speed of my own laptop, which right now is 5 years old, my own laptop is in fact faster than all of these supercomputers. Back then, these supercomputers were basements, okay, were as large as what I showed before. And now my laptop is faster than the fastest supercomputer of 1996. Again, my laptop is 5 years old. And it was faster than the 500th supercomputer in 2004 or so. So this is to say that, all right, sorry. This is to say that every computer is a supercomputer. And another message is that every computer is highly parallel. This is an analogy that I'm drawing with a highway. There are lots of lanes. In fact, in computers, there are also lanes. They're named, I guess it's not a coincidence, named alike. And the question I have is, are you driving your supercomputer like this, or possibly like this? Very likely like this, because there are only few people in the world that are able to actually organize a computation like that. This is by no means a trivial task. And again, I want to continue with this analogy of cars. If you think of a computer as, or a supercomputer as a car, you should think as a supercar. Your computer, your laptop, your desktop, it's a supercar. However, there is no way that you can drive a Formula One car, racing car. Very likely you drive it like this, like a tricycle. And there are very few people in the world that can drive a supercar like to its maximum potential. And the same for computers. And the way out is to collaborate. So that's the moral of the story, what I'm basically preaching, that you guys should continue doing your analysis, your investigations in bioinformatics. You should not try to become experts in high performance computing or in computing, in algorithms. That's what we should be doing, but it would be great to have collaborations. I want to give two examples. These are personal collaborations, personal experiences. One was with Yuri Olchenko, back then was a professor, now has a company, which Polyomica, which sounds like very much what Kate described, that same type of services. And he approached me to perform some very large scale genome-wide association studies. I for sure don't have to explain what the topic is to you, but I want to say that when he approached me, we could not understand each other. He was talking about GWAS, he was talking about mixed models. I had no idea what he was telling me. Then we, after several iterations, we converged to a common language, generalized least square problems. We were able to actually draw very clearly on the board what the problem is, the size, dimensions, what inputs are fixed, what change, how many times these problems have to be repeated. And it turned out, it became clear that they had really, really large problems, but they had a lot of structure. So over here, each single column here is the result of a generalized least square problems. Then the great thing is that you have to solve for all of these columns, but when you go from one to another along columns, some of the input data changes, but not others. And when you go by rows, other input data changes, but not some. And if you look at the problem as a whole, you can get a lot of savings, a lot of shortcuts in terms of avoiding redundant computation, making smart decisions. We did all of that. This was quite a long and fruitful collaboration. And in the end, what was basically unfeasible, these are extrapolated times. These are algorithms that were commonly used, all published in Nature, in fact. And we had more than 1,000x speedups. How? Partly because we could use computers better, and partly because we could do algorithmic choices that were smarter than the others. And that was because we were looking at the problems as a whole, not one by one individually. Example number 2, before I let Pedro take over. This is an ongoing collaboration with Rasmus Bro, professor in Copenhagen in food science. So he's doing, his group, they're doing a lot of chromatography with mass spectrometry. Again, I don't think I need to explain that, but it's about identifying components in food samples. And the data that they have, it's a 3-way or 4-way data. So there is resolution time, a mass spectrum, and then a number of samples. And you want to analyze this data to try and extract a profile that then can be matched to known chemical compounds. And this is done with a machine learning technique known as tensor decomposition. There are different types of tensor decompositions, different flavors for different needs, and even the different types of tensor decompositions have a lot of different varieties depending on what kind of constraints you want to impose, what kind of data, the dense, sparse you have. And so he explained to us the workflow. And again, we saw that, first of all, there is very much man in the middle in this kind of approach. And what that means that the user has to run some experiments, some analysis, I should say, then look at the results, see if these results are meaningful, if they make sense, and depending on what they see, they have to run other analyses, and so on and so forth. Again, if you do it on a one-by-one case, if you execute this analysis one by one, you'll miss out a lot of opportunities. We did, this is ongoing, okay, but we are doing, again, the same approach. We're looking at the whole workflow and not as an individual black box, but we're looking at the whole thing, and we are able to accelerate, again, by better utilization of computers and by better choice of algorithms. We can take down the execution time, this is in seconds, from either 1 minute or 6 minutes down to just a few seconds. Moral of the story, you guys offer lots of interesting challenges, interesting computational problems. I don't think you should try to become an expert in high performance computing. It's a great opportunity to collaborate. And now I let Pedro take over and give actually a demo. Thank you again.
Hello, can you hear me?
Yes.
Yes, my name is Pedro Ojeda, and I will show you a couple of examples on how to use HPC2N. And first, let me share my screen. So here, as you can see, I'm running the Windows operating system, as many people do. And in order to connect to HPC2N, one can use the ThinLink client, which is a very convenient way to transfer you to work with your files on our platform. So here you see this is a software that you can install easily. You get the data from HPC2N in order to connect to it, like a username and the password. And once you do it, you will log in into the system, and here you can start writing your text files and load your data, and it's quite convenient. So as you may be familiar with, I'm using here the R Studio software, where you can port your R scripts. And here I'm dealing with one example that I will describe. And this was a collaboration that we did with a researcher at the chemistry department who contacted us in order to compute a measurement that it's irrelevant for them, in order to classify and detect chemical compounds that are toxic and are very common in the environment. This measurement is called the cross-collision section, and there is a device that can measure this value, but it's not that easy. Yes, and also not that it's a bit expensive to do that. So theoretically, one computes the cross-collision section by solving this complex integral, right? And this comes from physics. And in practice, how do we do that? Well, there are different techniques to solve this integral, and one of them is by using a molecular dynamics simulation, or by using a cheaper approach, which is Monte Carlo. So basically, in molecular dynamics, one computes different trajectories. There are two molecules, and one propagates the Newton's equations in order to detect the angle at which these two molecules are scattered. So one repeats this process over and over, like 100 or 10,000 times, and one puts the scattering angles into this integral, and one computes the cross-collision section, which can be seen as a effective area of the compound. Yeah. So this measurement, the cross-collision section, is very precise and accurate, and it allows us to distinguish between even isomers of the same compound. So some of the compounds that Christine mentioned to me were these that are cited here, and there are only 27. We were studying more than this, like 50 compounds. So in theory, that's very straightforward to do, but in practice, these two approaches that I mentioned, which are molecular dynamics and Monte Carlo, are quite expensive because in the case of molecular dynamics, one needs to generate many trajectories, right? And also a more fundamental issue is that one requires a empirical force field. And with this, we need to determine several empirical parameters, right? And these parameters, if they are not found in the literature, we need to deal with them. For instance, imagine that you have a rare atom like uranium or some other atom that is not reported in the literature. We need to go to lower levels of theory like DFT and parameterize that. So that's not very convenient. So I thought that we could use a kind of machine learning to predict the cross collision section instead of computing them. And this is one of the compounds that we studied. This is called phenuron. And you see here the measured CCS value, and this 133. And with Monte Carlo simulations, we got this value 130, and molecular dynamics, this a very close value 130 as well. So how to use machine learning in this context? Yeah. So for machine learning, we need some input values that can be used as features, right? And some output values that could be used as the output or the response function. So basically, we go through some parameters space, and then we make some prediction. And we, in particular, are interested in the cross collision section. So for the input parameters, we decided to use the atomic masses because they are known, and also the Cartesian coordinates. There are several databases with the positions of the atoms in the compounds, like for instance, in this case, phenuron. And based on these two features, we will look at predicting the cross collision section. So the approach we follow was similar to the one in this paper, Physical Review Letters from 2012. And here they use a matrix called the Coulomb matrix, which is constructed based on the charges of the atoms. Because we are here not really interested in the charges of the atoms, and something which is more general are the masses. So I use this matrix, the masses of the atoms instead of the charges of the atoms. So this matrix is computed in this way. And then we need a measurement on how the molecules are similar among each other. And for this, we compute in a so-called Euclidean norm, which is constructed based on the diagonalized matrices. Using this measurement, we can compute a cost function, as we saw in the previous talks. And here we can plug in this Euclidean norm, and the only parameters left are these alpha values, which then need to be obtained through a minimization process. So this is done using the kernel-rich regression, and basically we minimize the cost function as in any other machine learning, and we add some penalization or regularization the term to avoid overfitting, right? So that's the theory. So this is the problem that we need to solve, a minimization problem, and this is the so-called training phase. As you may have seen here, this is a shallow machine learning type method. So here I'm showing you how to solve this problem in R, which is installed at HPC2N, and there are several versions. And here I'm loading the data, basically, as you normally do. And here I'm renaming the data so that I can compute the masses of matrices that I mentioned before. And at this step, I go into a loop to compute the similarity among all the molecules, right? And this is the most expensive part, which is also related to the training. And basically, the most difficult part is the diagonalization, which is a linear algebra operation, and it's quite expensive in machine learning. And once you train the model, and this means getting the alpha parameters that I mentioned before, then one could go to the prediction. And in the prediction, we use only 2 molecules, right? I mentioned before that we had 27. Then I used 25 for training the model, and then the last 2 to get the predictive values. And here you can see how they look like. For the prediction value, I got for a molecule 26, 171, and the measured value or the reported value in the literature 175. It's not that far from each other, and it's similar in the case of the molecule 27. So some comments from this simulation is that although the database is quite small, it's just 25 molecule for a training data set, we are already seeing some good performance of the model. Another thing is that all these molecules have a different number of atoms, and also the atom types are different among the molecules. And even in this case, we are seeing a very close CCA's value with respect to the reported one. The second comment is that I used as a toy model, as a toy machine learning model, this program to predict molecular dynamics trajectories, and I found that one could do it for a few time steps after the training data set. So this is what I had to say for the first model. And now let me go to something more standard. And here I will talk about the modified National Institute Standards and Technology database, or better known as the MNIST database. And this can be seen as a Hello World program for machine learning and also deep learning. So in this database, we can find 70,000 images, which are divided in a training and testing data sets. And each image consists of a 28 times 28 pixels box. And if you look at them, the picture looks like this one. They are handwritten numbers, and the goal of the algorithm is to predict the number of the digit that if you write a new one, right? So one can use different software for solving this problem. And in particular, we can use a Keras, and you may have observed here that I will be using R combined with Keras and TensorFlow, which are here. I'm loading the packages, and then the MNIST database is already included in the Keras package, and that's why I can load directly the database. So the data is already here, right? And because we are using a high performance computing center, we need to specify the number of CPUs, and this can be done in several ways. And for instance, you can request here a number of cores, right? In this case, 2. And once we load our data in machine learning, we need to divide them into the training and testing data sets. So these data are already loaded. And you know that we can, in general, not use the data set as in a raw manner. We need to make some transformations to the data initially. So this is done by reshaping and also rescaling the data so that they look in an appropriate way for a machine learning algorithm. So once we do some cleaning of the initial data, we can define the model. And in Keras, this is done by the model sequential method. And here we define the layers that we want for our model. So this model will be using a neural network approach, right, with 3 layers and some parameters defined here. So then we get a summary of the model, right, and the parameters that we will be using. And then we can compile the model. So in this phase, we generate some objects required by the library TensorFlow. So the model is now compiled, and when it is compiled, we can go to the training phase. And this is the most expensive part. If you see here, I'm just running that in a few, less than a second. But this part, the training, will take most of the time. And this is why HPC resources are very useful, because for this simple example, just a few images, and this is a Hello World program, you may use a laptop. But for realistic problems, if you have a large database and also millions of parameters to optimize, then a good way to do that would be probably the HPC resources. So let me go to the training phase. And in the meantime, we will use some tensor board displayed. So the training of the algorithm started, and here I'm displaying a tensor board. That is a useful tool for analyzing the output from TensorFlow. And you can see that the model is being trained, right? And this is the number of epochs which are required to optimize the parameters of the model. And you can see how your simulation is evolving, right? So an additional feature of TensorBoard is that it allows you to explore the type of network that you have. For instance, if you go to graph, then you can see the details of how your network is constructed. For instance, if you go to sequential, you can see how it is built and what you included in the model, right? This is a more specific tool that you can use with TensorFlow. And then once your model finishes, you can detect the accuracy and also the loss of the model, right? So this model is divided into a real training data set and some validation set by specifying the parameters in TensorFlow. Here, for instance, we are splitting 20% of the data as a validation set to get the loss and the accuracy. So here, R also provides you with some light way to explore the evolution of the model, and the output reported by R looks like this. It's more simple, but it's also convenient if you don't want to deal with TensorBoard and if that is too much information for you. So you can see also the loss on the training data set and the validation set, and also the accuracy, right? So, and finally, we can evaluate the model. And in this case, we see a accuracy of 98, right? And this is a sample of how the predictive values look like. Yes. And another take-home message is that here I'm combining different software, because in machine learning and deep learning, in general, we can combine different software in order to get a more accurate and precise answer, right? Here I'm combining R, and I'm calling Keras and TensorFlow, but R can also call Julia, which is also coming in these years. Okay, that's what I had to say. And if you have any questions,